Morning to all. This is DNL Sai Vishnu. I am from CSC Data Science B section. Today, I am discussing about the applications of filter theory, design of reactance. This PPT, we are we are discussing about history of the filters, classification of the technology, passive filters, active filters, L, L filter, T-shape filter, transfer functions, classification by design methodology. Next slide. First of all, we will discuss about introduction of filters. Filters, as the name suggests, they filter the frequency components. That means they allow frequency components and or reject some other frequency components. Electronic filters are type of signal processing filters in the form of electrical circuits. This article covers those filters consisting of lumped electronic components as opposed to distributed element filters, that is, components and interconnections that in analysis it can be exist at single point. These components can be in discrete packages or part of an integrated circuit. Electronic filters remove unwanted frequency components from the applied signal, enhances wanted ones, or both. They can be passive or active, analog or digital, high pass, low pass, band stop, or all pass, discrete time or continuous time, linear or non-linear, infinite impulse response or finite impulse response. The most common type of electronic filters are linear filters, regardless of each other aspects of the design. See the article on the line linear filters for details on their design and analysis. The introduction of filters is completed. Now we'll move to next slide. History. History of the filters tells that the oldest forms of electronic filters are passive analog linear filters constructed using only resistors and capacitors or resistors and indicators. These are known as RC and RL single pole filters respectively. However, these simple filters have very limited use. Multipole LC filter provide greater control of response form, bandwidth and transition bands. The first of these filters was the constant K filter invented by George Campbell in 1910. Campbell's filter was a ladder network based on transmission line theory. Together with improved filters by Otto Zobel and others, these filters are known as image parameter filters. A major step forward was taken by William Core, who founded the field of network synthesis around the time of World War II. Core's theory allowed filters to constructed that precisely followed some prescribed frequency function. This is about the history of the filters. Now we'll move to the classification by technology. First one, passive filters. Passive implementations of linear filters are based on combination of resistors, inductors, and capacitors. These types are collectively known as passive filters because they do not depend upon the external power supply and they do not contain active components such as transistors. Indicator block high frequency signals or conduct low frequency signals while capacitors do the reverse. A filter in which the signal passes through an indicator or in which a capacitor provides a path to ground parentless attenuation to low frequency signals than high frequency signals, and it's therefore a low pass filter. If the signal passes through a capacitor or has path to ground that an indicator, then the filter presents less attenuation to high frequency signals than low frequency signal and therefore is a high pass filter. Resistors on their own have no own frequency selective properties, but are added to inductors and capacitors to determine the time constants of the circuit and therefore frequencies to which it depends. Next slide. The inductors, capacitors are reactive elements of the filter. The number of elements determine the order of the filter. In that constant, an LC tuned circuit being used in bandpass or bandstop filter is considered a single element even though it consists of two components. At high frequencies, sometimes the indicator consists of single loops or strips of sheet metal, and the capacitor consists of adjacent strips of metal. These inductive or capacitive pieces of metal are called stubs. Single element types. This is the another type of filters, passive filters. The simplest passive filter RC and RL filters include one reactive element except hybrid LC filter, which is categorized by inductance and capacitance integrated in one element. Now we will move to another type of another shape filters. In this shape filters, we will know about L filter and T filter. First, we will discuss about L filter shortly. An L filter consists of two reactive elements. One is series and one is parallel. Now, the T-shape filter we will talk about. Three element filters can have a T or pi topology and in either geometries. A low pass, high pass, band pass, or band stop characteristics is possible. The components can be chosen symmetric or not depending on the required frequencies characters. The high pass T filter in the illustration has a very low impedance at high frequencies and very high impedance at low frequencies. That means that it can be inserted in a transmission line resulting in high frequencies being passed and low frequencies being reflected. Likewise, for the illustrated low pass pi filter, the circuit can be connected to a transmission line transmitting low frequencies and reflecting high frequencies using M-derived filter section with correct termination impedance. The input impedance can be reasonably constant in the passband. Now we will move to the next slide. Multiple element types. Multiple element filters are usually constructed as a ladder network. These can be seen as a continuation of L shape, T shape, and pi shape designs of filters. More elements are needed when it is desired to improve some parameter of the filter such as stop band rejection or slope of transmission from pass band to stop band. Active filters. These are another type of filters that are which are independent to the source power. Active filters are implemented using a combination of passive and active components required an outside power source. Operational amplifiers are frequently used in active filter designs. These can have Q factor and can achieve resonance without the use of inductors. However, their upper frequency limit is limited by bandwidth of amplifiers. Now, in previous slides we discussed about various type of filters, what is meant by active and passive filters, those. Now we'll move to the transfer function of a filter. The transfer function of filter is the ratio of output signal so that of input signal as function of the complex frequency. There is a formula to derive the transfer function of a filter. The transfer function of all linear time invariant filters when constructed of lumped components will be the ratio of two polynomials in S, that is a rational function of S. The order of the transfer function will be highest power of S encoded in either numerator or denominator. This is the topic based upon transfer function and how to derive a transfer function of a filter. Now we will move to the design methodology of at next slide. Next slide. Classification of design methodology. Historically, a linear analog filter design has evolved through three major approaches. Oldest designs are simple circuits where the main design's criteria was Q factor of the circuit. This reflected the radio receiver application of filtering, as Q was measure of the frequency selectively of a tuning circuit. From the 1920s, filter began to design from image point of view, most of the being driven by requirements of technology, telecommunications. After World War II, the dominant methodology was network synthesis. The higher mathematics used originally required extensive tables of polynomial coefficient values to be published, but modern computer resources have made it that necessary. Direct circuit analysis. Low order filters can be designed by directly applying basic circuit laws such as Kirchhoff laws to be obtained transfer function. This kind of analysis is usually only carried out for simple filters of first order and second order. This is a graph for RL filter frequency response. We will move to the next slide. Image impedance analysis. This approach analyzes the filter section from the point of view of the filter being in an infinite chain of identical sections. It has the advantages of simplicity of approach and the ability to easily extend to higher orders. It has the disadvantage that accuracy of predicted response relies on filter terminations in the image impedance, which is usually not the case. There are four image impedance analysis. First one is constant K filter response with 5 elements. Second one is Sobel network filter, 5 sections. M derived filter response when M is equals to 0 for 2 elements. M derived filter response M is equals to 0.5 for 5 elements. These are the four image impedance analysis. Now, next slide. Network synthesis. The network synthesis approach start with the required transfer function and then expresses that as a polynomial equation of the input impedance of the filter. The actual element value of the filter was obtained by continued fraction or partial fraction expansion of the polynomial. Unlike the image method, there is no need of impedance matching networks at the terminations, as that effects of the terminating resistors are included in the analysis from the start. Here is an image comparing Butterworth-Chebyshev elliptical filters. These filters in illustration are all fifth order or low pass filters. The particular implementation, analog or digital, passive or active, makes no difference. Their output would be the same, as is clear from the image. Elliptical filters are sharper than all others, but they show ripples on the whole bandwidth. The graph of the four filters shows that elliptical filters are sharper, and also they have a disadvantage that they show ripples on the whole bandwidth. This is small, and they affect slight disturbance of the frequencies. Now we'll move to the next slide. Conclusion. In this discussion of work of a designing approach of active filter is proposed, the departure of actual OP amplifier from ideality at higher frequencies restrict active filter applications below MHz. In filtering is done by the RC network. In the active filter circuit, the quality of Q factor is more sensitive to component tolerances. Very small change in component value due to drift or again leads to large variation in Q factors in active filters. To study the effect of small variation of component value, two parameters M and N are taken into consideration and its effect the frequency response of filter circuits is studied due to increase in the value of M and N. The gain is peaking is observed exactly at F, O. For low Q factor, the transitions from one asymptote to the other is very gradual, while for high Q factor, there is range of frequencies in the neighborhood of where filter provides gain. These phenomena refer to peaking. Such peaking responses are useful in the synthesis of permanent filters for the simulation of the human vocal tract. Frequency responses for different values of M and N are studied. For higher values of M and N, the gain peaking is observed. That is, Q increases indicating a high degree of selectivity. In band reject filters, it is noticed that the top notch depth is maximum for Rs is equals to R by AB. The notch depth of band rejects filters depends on the resistance R3 which is used in the input of summing amplifier. The frequency response of bandpass filter shows that the gain bandwidth products remains constant. For higher Q, the response become narrower. That means more selective the filter. This is the conclusion for the network theory and reactance network, in which we studied about the introduction, impedance, types of filters, characteristics of filters, and image impedance, network synthesis, classification of methodology, and conclusion. From these, we analyzed the network. Ne- we analyzed the network reactance of filter theory. Next slide. Thank you. Thank you for giving this golden opportunity. Hope you liked it.